So the organizer kindly didn't ask me for a title, but I hope I chose a subject which is consistent with the general theme of this workshop, summer school, whatever official thing we are currently doing is called. So, what do I mean by rigidity properties of diagonalizable actions? Well, Manfred has been telling you quite a bit about how unipotent flows work. There are various very special properties. Every orbit has to behave in a very strict way. They don't have much choice. And I think maybe in the first day in his lectures, Manfred probably also mentioned that for the action of the diagonal group on SL2R modulo SL2Z, things are much different. Every point basically can do whatever it wants. A typical point would behave in a very prescribed way. The orbit would be equidistributed in the space according to Lebesgue measure, but individual points may do whatever they please, more or less. Now, it turns out that perhaps this is true for one parameter diagonalizable actions in fairly big generality, but once you have already two commuting diagonalizable actions, things are quite different. And this has been observed in very different settings by Furstenberg from the dynamic point of view, which would be also my point of view, but in some implicit way also by Cassels and Swinnerton-Dyers already in the 50s. In any case, here's sort of a starting point for my talk is the following. Not very difficult, but it turns out a very influential theorem, very fundamental insight of Furstenberg. And this is from 67, I believe. So, the theorem says the following. Suppose I have a set F inside R modulo Z, so like Manfred, I'm looking here at a Lie group G divided by lattice gamma, but my Lie group is a fairly simple Lie group, and my lattice is a fairly simple lattice at the moment. This is a closed set, and on this R mod Z, there's of course the action of integers by multiplication. So let me just maybe add here someplace some small notational remark. So for x in R mod Z, I'm going to use n acting on x to denote nx mod 1. In general, something point something would be denote an action, and you'd have to figure out which action I'm going to use. So suppose we have a set which is closed, and suppose that it's invariant under multiplication by two multiplicatively independent integers, by which I mean that if I take my set and apply on it this multiplication by n, it will be contained in itself. Of course, equality is allowed. And same is true for another integer, and of course I want to actually say that these are different integers. So I'm going to say that n and m are multiplicatively independent integers. Independent integers, which for instance means that n to the k is not equal to n to the l for integers k and l, unless of course k is l is 0. So I have two multiplicatively independent integers, then either F is finite, or F is everything.
Excuse me?
Yes.
What is multiplicatively independent?
M to the k is not equal to m to the l unless k equals l to c.
That's the definition.
That's the definition. If you prefer, you could say that the logarithm of n divided by the logarithm of n is irrational. Of course, the same. Okay, so that's the theorem. And of course, this contradicts quite drastically with what happens if you take a set which is invariant under multiplication by only one integer, say n equals 3, right? If you take the ordinary Cantor set, it's invariant under multiplication by 3 modulo 1. So there are very many sets, if I just have invariance under one multiplication by one integer, there are very many closed sets which are invariant. But somehow, once I have these two commuting actions, they give much bigger rigidity. There's much fewer choices of orbit closures, and this also implies that if I take a point and look at its orbit under multiplication by n and multiplication by m, it has only few ways it can behave. And he also gave a conjecture, though never, as far as I understand, in print, that if we use the probability measure, on R modulo Z, and which is invariant under multiplication by n and multiplication by m. So now this is a different action. Right now I'm looking at the action of the semigroup of integers on the collection of probability measures on R mod Z. But again, it's an action, so I use the same notation that I've used. N and m are again multiplicatively independent. Then either mu has atoms, so there exists some x such that mu of the singleton x is positive, or mu is Lebesgue measure. Lebesgue measure I would always denote by m, and some arbitrary measure I don't know much about would be denoted by mu or any other Greek letter. Now, this conjecture is still open. It seems fairly difficult, at least some people have thought on it for some time. But these thoughts did not come out empty-handed. Following some preliminary results by Lyons, we have the following theorem by Rudolph and Johnson, which says that if mu is as the conjecture, mu is as in the conjecture, and the measure, let's say the entropy of mu with respect to the times n map is, let's say, bigger than 0. Let's say it's actually equal to alpha times to normalize things, let's say it's actually equal to alpha times the maximum such entropy can be, which is logarithm of n. Then mu dominates alpha times the Lebesgue measure. Okay, this means that mu of any set A is at least alpha times the Lebesgue measure of the set A. This is not the usual way of stating the theorem, though it's equivalent to it quite easily. Equivalent formulation, so equivalent formulation is to assume that mu is n invariant in the sense above, probability measure, and assume that mu is ergodic under the action of the full semigroup of a multiplicative semigroup generated by n and n. Okay, by which, what does ergodic under a semigroup mean? It means that if I have a set which is invariant under this whole semigroup, so if x is inside my set, then n to the k, m to the lx is inside my set. If I have such a set, it would have measure 0 or 1. That's what ergodic means in this context. Then assume also that the entropy, let's say, of the times n map is positive, then mu is a big measure. And why does this, say, follow from this? Well, you know, or should know, that ergodic measures are either equal or would be mutually singular, and they can't be mutually singular because of this statement. So if I have a measure which is ergodic under this action, it has to be actually, with positive entropy, it has to be equivalent to the big measure. Okay, so I would like to explain to you first, maybe the first thing I'd like to explain to you is the proof of this theorem, but I prefer to look not at this theorem but at a analog of it. An analog where I think one sees a bit better what happens. One thing which is slightly annoying about this dynamics on the circle is that it's not invertible. So far, most of what has been talked here has been about group actions. Groups will actually have inverses. The integers, or more precisely the natural numbers, the multiplicative structures, of course not a group but a semigroup. I would like to talk about a group. So here's an analog which is it's an analog. It also has some new features which will be quite interesting. Analog Z2 actions on a d-dimensional torus by automorphisms. And of course, what is an automorphism of the torus? An automorphism of the torus is given by an integer matrix. So this action will be generated. So the action will be generated not by integers, of course, by two matrices, A and B, inside S L D V. I guess there's no real reason to restrict the determinant to be 1 and not -1, but makes no difference. And I want to assume that it's actually a Z2 action, not something much smaller, so I assume that they are multiplicatively independent in the same sense as before. No power of 1, no non-trivial power of 1 is equal to a non-trivial power of the other. And I guess none of them is identical. So here's a theorem in this case, which actually requires, in this generality, some extra ingredients. It sort of goes a bit beyond what you'd have in the Rudolph-Johnson theorem. So it's based on many similar ideas. And the theorem, I guess, in this form I'm stating it is Einzigler and myself. But in many cases, very many cases, you could basically follow the work of Katok's Tzir, and maybe I also mentioned Lenin. Katok Lenin, there's also some extensions. So anyway, this is the theorem. So under these assumptions, so suppose we have all these assumptions, so I have this action by multiplicatively independent matrices. Suppose mu is invariant plus ergodic under the action of the group generated by A and B.
A and B commute?
Yes, I should say so. Multiplicatively independent, A, B equals B, A. Otherwise, we are dealing with a very interesting question, which I would probably one would tell us quite a bit about, but definitely not a Z2 action. So to get a Z2 action, you need to assume that A and B are commuting under the action of the group generated by A and B. And mu is also a probability measure. With entropy of some element of the action, regardless of generalities, I take to be A being positive. Now I need to make some assumption, some kind of irreducibility assumption. If I really want to sort of conclude that the invariant measure has to be the Lebesgue measure, which would be my last line, I have to make some additional assumption. The assumption I need, both necessary and sufficient under these circumstances, is assume that the group generated by A and B acts, I don't know if it's totally or strongly irreducibly on TD. I have now enough experts to answer for I know whether it's totally or strongly irreducibly. By this I mean that there's no positive dimensional subgroup of TD invariant under a finite index subgroup of the group generated by A and B. Okay? There is no subgroup, let's call it Y of TV, closed, dimension of Y positive, which is invariant under a finite index subgroup of the group generated by AB. Okay, some irreducibility assumption. Then mu is the Lebesgue measure. This is an analog, close analog of Rudolph's Johnson theorem. Now I'm not going to prove the general case. I want to prove one instance of it. So the case we will look at my torus would be 4-dimensional. D would be 4. So I'm looking at two 4x4 matrices. And one of them, so, and A and B would have each of them two real and two complex eigenvalues. And moreover, and they would be totally reducible, etc., everything that's there. And I want that the eigenvalues, the complex eigenvalues for A have absolute value 1. Okay, so for instance, if you look at the polynomial x to the 4th minus 5 x cubed, I hope I copied this correctly, minus 2x squared minus 5x plus 1. So the roots of this polynomial have, there are 4 roots for this polynomial, that's not too surprising. Polynomial is irreducible over the rational numbers. There would be 2 real roots, there would be 2 complex roots. The complex roots would have absolute value 1. And then I can take, if I want A to be basically any polynomial with this characteristic polynomial. Hopefully, I haven't taught linear algebra for some time, but hopefully this is the right thing to choose. And okay, this B, and there will be some B. I was too lazy to find a particular choice of B. But anyway, this thing. This is not a vacuous case. It's a special case, it's not a vacuous case. And okay, so I want to prove to you, in this particular case, I want to prove to you that if I have a measure which is invariant under ergodic under this Z2 action, if it has positive entropy for some element of the action, it has to be Lebesgue measure. Questions so far? Is it clear what we're trying to prove?
So if you take this statement and you erase the positive entropy assumption, the conjecture would still be that
yeah, the measure should be either finitely supported or a Lebesgue measure.
because somehow from the positivity of the entropy you have some hyperbolicity conclusion, and you didn't build it into the statement, but you still.
Well, I think this would follow from. I think if you have a totally reducible action, you certainly have some eigenvalues which would be non-zero, right? Somehow. Some Lyapunov exponents would be non-zero. This just comes from being totally reducible and determinant 1. Okay, so we want to prove this, and I guess if you want to prove something and somehow entropy makes an appearance here for reasons which I have not explained explicitly, in part because I am not sure I understand why entropy really should enter in this classification in a very good way. But anyway, we want to use entropy, so I should maybe review a bit about entropy. So here's a bit of review about entropy. Review on measure theoretic entropy. understand that Alex talked a bit about entropy, so I'm really reviewing things which have already been said here. So I have an abstract measure preserving system. X, mu, b, t. This is an abstract measure preserving system. And I have a partition P. P would be, let's say, countable partition, countable or finite partition, or finite partition. But not every countable partition will be good for us. I'm assuming that the entropy of this partition is finite. I remind you that the entropy of a partition, one way to think about it is expectation. If I take a random element according to mu, I look at the atom, this point x lives inside P, so this is this notation here, but this is the element P in P containing x. Some people denote this as P of x, but this would be a reasonable way of denoting it, and this is the entropy of the partition. It's of course equal to the usual definition of summation pi log 1 over pi, but this is maybe a nicer way to look at it. So this is the kind of partition we look at. Definition: P is generating partition, is a generating partition. If I would look at those points at the atom of x according to the sigma algebra generated by translates of P, which is by definition, if you don't like atoms of a partition, countable generated partition, this is by definition the set of all those y's inside x such that y, such that t to the I y, the element of the partition P containing t to the I y is the same as the element of the partition P containing t to the I x for all I. This is by definition what this symbol means. So in generating, if this is the singleton x, let's say for all x things. If you have a particular measure in mind, perhaps you could weaken this by putting almost everywhere various places, but maybe for measure classification purposes, it's better not to put almost everywhere where it's not needed. So this is what a generating partition is, and then there's the theorem of Kolmogorov and Sinai. That if I take the following limit, which obviously exists by subadditivity properties of the entropy functional. So this exists by definition. This exists all by, this is, it really exists. That's not a theorem. H mu of the partition generated by translates of P. This quantity does not depend on P, it's actually they depend on P, and is equal to the if P is generating, right? And it's equal to the entropy of mu T, which by definition is the supremum over all partitions P with countable partitions with finite entropy of this quantity. So maybe I should here put here a prime to make clear that I'm different. Okay, this is one of the most basic theorems in entropy theory. Before you have this theorem, you basically cannot calculate the entropy of anything. And now there's a miracle in entropy theory, which it's easy to somehow overlook it, or overlook how surprising it may be. Here's sort of a small miracle. And of entropy theory. So you can find the past tail and the signs I somehow had. For the partition P is basically, so you take the sigma algebra generated by t to the minus ip I from minus infinity to minus n. These are basically all sets, all Borel sets you could determine membership of by knowing which element of P t to the kx is for all k bigger than, I guess here all k smaller than minus n. And now I take this intersection of all n. Okay, this is one tail. This is somehow all things you could determine from knowing where t to the minus kx is for x large. And there is a future tail. So this is certainly a sigma algebra. And this is another sigma algebra, which basically is all things you could determine by things knowing where your point is in the far future. And these two tails, so the minor miracle is, let's call it a theorem, or no, let's call it a theorem, that these two sigma algebras, which a priori are very different, and indeed they're somehow abstract Borel sigma algebras, they are quite different, but with respect to an invariant measure mu, they are essentially the same. So what this notation means, so again I need to put here a small bubble. If I have two sigma algebras and the measure, these two sigma algebras are equivalent modulo the measure if for all A in A, I can find a B in B such that the measure of the symmetric difference is 0 and vice versa. Okay, so this is what this symbol means. So the past tail and the future tail are the same, and this also coincides, and if P is generating, then these are the Pinsker, then tau plus or minus P are up to mod n the largest zero entropy sigma algebra, a sub-sigma algebra, by which I mean, to be more explicit, if I have some factor map, if phi for my x b mu t to y c mu s is a factor map, to some let's say standard Borel space, this is sort of the Borel subsets of some Borel space in a complete space. That's what the standard Borel space is. And if the entropy of nu with respect to S is 0, then I take this sigma algebra of the factor, I lift it to my space. This will be contained again up to sets of measure 0 inside this whichever tail you wish to use for your partition. And conversely, if for some factor the inverse C is mod 0 sets measurable with respect to the tail, then the entropy is 0. Okay, so this is some kind of this is a miracle, and this is the explanation that you could identify both of these tails somehow with some universal sigma algebra, the maximal sigma algebra, according to which every measurable, every factor which is measurable according to it would have 0 input. So I guess 1 is a miracle and 2 is explanation, if you wish. By the way, this kind of statement there's a nicer way to say it. It's an equivalent way to sort of think why it's equivalent. Slightly nicer way of saying this, which would be useful for us later, so I'm going to say it. Slightly nicer way of saying this is that there would be some set x prime inside x of full measure. Such that if for some n, if let's say you have 2 points x and x prime in this set of full measure, little x and little x prime inside this big x prime of full measure, and for some n t to the ix is t to the ix prime, and it's like the same atom for all I greater than n, then phi of x is equal to phi of x. And that's basically the same way of saying the same thing. In different ways. Okay, so this was a long detour, or at least a detour. Let me illustrate. I would like to illustrate what this actually means in illustrate what this means in the case of, let's say, a hyperbolic toral automorphism. And hyperbolic is needed here in a very, very big sense. That is to say, it's not needed, but to say in a couple of words, if I would assume that my automorphism is hyperbolic. So let's see somehow here sort of a visual interpretation of this entropy miracle for a hyperbolic toral. So A is some integer matrix, right? A acts on PD, which is RB modulo VB, and then what does hyperbolic mean? Hyperbolic means that I can write RB as, let's say, V1, V plus V minus, and for some lambda hyperbolic, it means that there's a splitting, and there's a lambda bigger than 1, and so for every little v in V plus, AV is bigger than lambda v, and if v is inside V minus, AV would be smaller than 1 over lambda. That's what hyperbolic means. Under these assumptions, it's quite easy to identify generating partitions. So under these assumptions, under the hyperbolicity assumption, any partition P with mesh, so there will be some delta positive, so that any partition P with mesh of P smaller than delta is generated. Where I remind you, the mesh of a partition is the diameter of the biggest element. Okay, this upper is the biggest diameter of one's element of the partition.
Do you really mean the same lambda with the lambda and 1 over lambda?
Why not? I'm not claiming it's optimal in any way. Some lambda. Okay, so I have this. So this is a partition. Let's assume that P is such a generating partition. Assume that in addition, maybe P is a finite partition. Assume that P is a finite partition with small mesh. Let's assume in addition a slightly technical condition that if I take the measure of those points x inside the torus, such that if I take the distance between x and the complement in the torus of the element of the partition containing x is less than, let's say, eta, the measure of the set is less than c eta to the alpha for some c and alpha point. Okay, so I'm assuming that somehow typical point is not too close to the boundary of the partition element containing it. this is quite easy to arrange. So one easy way to construct such a partition, so this is relatively easy to arrange because you could, let me maybe write this down. Such partitions are relatively easy to find. Easy to find. Here's how. First partition, so take P1 as a partition of the d-dimensional torus into small cubes. Into cubes of diameter less than this delta that I want to be less than that. So, okay, this is a partition. Nobody told me to satisfy this condition. But if I translate this partition for somehow Lebesgue almost every choice of shift, if I take all of the elements of P and shift them by C, this P, which is P1 plus C, will work. Okay, so it's quite easy. This assumption is certainly a non-trivial assumption, but again, there are such partitions. Okay? So, if you look under these assumptions, here's a proposition that I'm not going to prove, but it's relatively easy. Under these assumptions, if I take any point x in TD, and I would look at the atom of its partition with respect to the sigma algebra, let's say, so this is the set of all points y, so that t to the I y and t to the I x are in the same element of the partition for all I positive. Okay? Now, this means that somehow, so again, this would be inside x plus this stable manifold for x, for v. This will be inside there because if y is inside this thing, then in particular the distance between t to the I y and t to the I x would be less than delta for all I positive. And if delta is small enough, then this would force the points to be on the same stable manifold. Otherwise, it would be even a bit different in the unstable manifold. When you apply enough t to the I, suddenly they would be different by, I don't know, at least quarter distance or something. This required only this mesh assumption, as in some sense exactly basically determines my choice of delta. But two, which, and this uses this technical condition Let's use this technical condition on being far away from the boundary for mu almost every point x. If I would look at, there would be some positive number Rx such that inside this atom so this collection of sets, this collection of points which stay in the same atom like X in the future trajectory would actually contain a small ball in the unstable direction, a ball of radius Rx in the unstable direction around 0.
Excuse me, okay.
Questions?
Do you mean V plus there? In the bar?
I think I mean V minus because
So this is V minus as well.
this is V minus. This is V minus.
Is it the same from the hyperbolic?
Yes,
So
it's the same. So these are, think about it, if 2 points differ in the V minus and they go forward in time, they would tend to be closer and closer. Because there's a good chance they would be in the same element of the partition.
Maybe the confusing thing is that taking inverse for the partition means taking future of points. T to the minus I p is the partition that corresponds to future times.
no, I think just the notation is the V minus
Minus
the
in
same
index is the same as minus.
the V minus
Yes.
from there?
Yes.
Because V minus-
The superscript and subscript are not.
yeah, that's the only thing.
Superscript and subscript are
Okay.
convey no information. Okay. So now, of course, one can expect, and of course this will be true, that if I take the things which now I get a bit lazy. Instead of recording where x is at every positive time, I sort of take a nap, wake up after 10 iterations have passed, and only then begin to record things. And of course, I'm more lenient in what I'm considering. So it's reasonable to expect that as n goes to infinity, this will include bigger and bigger, will include larger and larger neighborhoods of x on x plus v minus. Inside this, if you wish to think of it, the stable manifold through x, x plus v minus, all these points whose trajectory is asymptotically the same as x, this would include bigger and bigger chunks of it. And then using this observation and this proposition, one gets another proposition which I am which is I think, given the hints I've given so far, is quite easy. That for such a partition P, a partition with small mesh, and this technical condition on boundaries of elements of the partition, for such a partition P, if I would look at, let's say, now this was my tau minus, I think, according to my notation. Tau minus this position P, which hopefully was the intersection n for 1 to infinity V I n to infinity t to the minus IP is equal satisfies that it is modulo sets of zero measure. It is exactly the collection of Borel, sigma algebra of Borel subsets of TD, which are invariant under translations by V minus. Let me try to explain why this is plausible. Not why this is, not prove it, but explain why this is plausible. Okay? So I told you that if I have, so suppose I have some set measurable with respect to this sigma algebra Z. Okay, some set which is measurable with respect to sigma algebra t to the minus IP, I from 0 to infinity. Then this set, if it contains a point x, would have to contain all these points which are indistinguishable from x. It would have to contain, if it contains a point x, it would have to contain this small neighborhood. Okay? Now if I have a set which is simultaneously measurable with respect to all of these sigma algebras, which is precisely what it means to be in the tail, if it's simultaneously measurable with respect to all of these sigma algebras, then if it contains a point x, it should contain all of the V minus orbit of x. So certainly any set which is measurable with respect to the tail should, maybe after I fudge around by sets of measure 0, should consist of full leaves of the full cosets for this group V minus acting on the toes. The inverse is also quite easy, but maybe slightly more delicate. And of course, this is just equality modulo null sets. This is so that's nice and good. And similarly, from similar reason, if I look at T plus P, it would be essentially Borel subsets of TD, which are invariant under translations by V plus. And the miracle of entropy theory is that if I have any measure invariant under a hyperbolic tori automorphism, I look at these two very different sigma algebras, one of which is sort of invariant under translations in one direction, the other which is invariant under translations by another direction. These two different sigma algebras are in fact, modulo my measure, equivalent. Now, we'll take a couple of minutes from the break. I'll state maybe what my I'll try to tie back to actions of to Z2 action, and then we would and then I'll take a break. So now return to my action of the group generated by A and B, and A was somehow a bit special on T4, which is R4 modulo V4, and R4 I would write, there will be a one-dimensional space spanned by the eigenvalue of the eigenvector of A with real eigenvalue bigger than 1. Let's call this plus of A. And there will be a one-dimensional direction spanned by the real eigenvalue of A with which is contracting, and there would be a two-dimensional subspace which corresponds to the two complex directions, which of course is not an eigenspace, really an eigenspace, but in which A acts by rotation. And P also preserves this partition. It would also act on this by some contraction or expansion, on this by some contraction or expansion, and on this basically as a multiplying by some complex number, so it would be by some similarity transformation. And because the action is sort of, because A and B is a Z2 action, it's an honest Z2 action, because A and B are multiplicatively independent, then any way I can group, so for any way I can group, I take these two things, V plus A, V0A, V minus A, and I group them in some way into W minus and W plus. So maybe I take W minus as the sum of this and W plus as this. So any way I do it, there will be, but none of this can be empty. So there are not so many choices, right? I mean, both of them, each one of them should be at least one-dimensional. So it's basically 3 choose 2. So basically, there are 6 possibilities for this rotation. So for any way I group these, there will be some element gamma inside the group generated by A and B, such that gamma contracts W minus and expands W plus. So now I would like to use this entropy miracle, which just required one action, use the fact that I have a measure invariant under many elements, and basically I would like to deduce, so here's sort of the important lemma, which I will prove right after the break. And you can try to see if you could prove it during the break. If mu is AB invariant, then mod null sets, if I take the sigma algebra, so the V plus A invariant sets, Borel sets, is up to sets of measure 0 the same as the V minus A invariant set. This is just, this in fact is just, you need to be slightly more careful because it's not an hyperbolic transformation, but basically this is essentially follows the same argument I did, but it's also the same as these all of these, I don't just have now, because I have a bigger action, I get something somehow better. I don't just have equality between two unrelated objects, but now I have equality between three unrelated objects. So this I'll prove after the break, and I'll also explain why this is a useful thing to have.
Are there any questions?
There are no directions which are neutral for A and B because of the total irreducibility.
Inside this group, so this is a two-parameter group, and there are basically three Lyapunov exponents, and the sum of them with the right weights should be 0. So basically, they need. That's one of the simple things about this particular case. You could expand any one or two of these three directions and contract the remaining one or two directions.
What are you using here? I'm a bit confused.
Here, basically this should just follow. Once you believe me that there are multiplicatively independent integer matrices, then basically this is.
But why couldn't it be that there is some subspace on which A acts by rotation and B also acts by rotation? So
then they would not be able to be multiplicatively independent.
It's also discrete. You somehow multiply by something with A, you multiply by something else in B. And if there's no third direction to come to the rescue, you get a contradiction to discreteness, or they are independent.
It's not so important. I mean, if you could have just assumed that this happened, which I could give you just A and B, which is this two, and just giving you a case. But as stated, what I said is correct.
Any further questions? If not, let's enjoy the rest of the break after thanking the speaker again.